Well, after we've had a bunch of algebra to go through, solving differential equations, I'm gonna interject some analysis of the differential equation instead, something a little bit different, and then we will get back to our differential equations. So the last problem we had, that the roots were at -3 plus or minus 3i. We could look at the 3 from what we know already, the -3, the real part. So the absolute value of the inverse is 1/3 of a second. So that's the time constant. 4 time constants is what we call our settling time. So there's 4/3. And we can plot this. Here's -3 plus or minus 3i. And of course, this was the characteristic polynomial for what we had. All right. Now, when we have complex roots, and I have to emphasize, complex. This doesn't apply if we had two real roots. We can rewrite this piece this way as lambda squared. Well, that's lambda squared is lambda squared. That doesn't say much. 2, this is a zeta. This is omega n. Here's another lambda plus omega n squared. What are these things? This zeta here, this is damping ratio. Okay, so this is how much damping is in the system. So if you have more damping, you'll get less oscillation. Okay, the amplitudes will go down. Natural frequency. Okay, this is in the region of the system's resonance. So this is the area where if you put some vibration in, it'll get amplified. Okay, think the Tacoma Narrows Bridge. You know, a little bit of energy comes in and just blows out. Okay, and then here's omega n squared. So same term as over here. So we can write this way. And so we want to take a look at what these things mean. So if we equate these, we can see the natural frequency, which is in units of radians per second. Here, 18 to omega n squared. Take the square root, 3 root of 2. Okay. Damping ratio. So if we know what omega n is, it's the square root of 18 from up here. So we have 6, 2 times damping times the square root of 18 equals 6. So we can solve for that. Works out to be the root of 2 over 2, or 0.707 for our damping ratio. Okay. And that is kind of a famous damping ratio, shows up a lot. But anyway, it is what it is. And if you were to get the roots of this thing, okay, we know they're -3 plus or minus 3i, but using these variables, if you were to solve for this, and you can multiply this out and check it out, you would wind up with, we know lambda is, the roots are -3 plus or minus 3i. They are also minus the damping ratio times the natural frequency, plus or minus, okay, omega n, the square root of 1 minus zeta squared, and we have an I out here. Or we can call this whole piece omega d I. And so what significance is that? Okay, this omega d here, we'll just go down a little farther, is called the damped natural frequency. And why is that important? So omega n is in this region of resonance, and omega n actually has, when we get into frequency response, we're going to see it has a very specific meaning. But for now, we'll just say it's in the region of resonance, which is true. Omega d, the damped natural frequency, right? When this system responds to a step input, there will be a response that looks like this. Okay, this frequency here is the damped natural frequency. So it's the actual frequency of oscillation, I should say, for a step input, that the system will just naturally oscillate at. So we have damped natural frequency as your actual frequency of oscillation in your complementary solution. Okay. So we can plot these things out. So if you look at this, so if you were to plot the roots, here's -3 plus or minus 3i. omega d, that will be omega di, so that'll be 3. So this thing, if as it oscillates, that'll be at 3 radians per second. So let's just kind of plot this out, see what happens. So here's minus 3 plus or minus 3i. So here's the minus 3. That distance is zeta omega n. This height is omega d. And if you were to multiply this out, square this plus this, so this squared plus this squared, guess what? It's omega n squared. A squared plus b squared equals c squared. This distance squared plus this distance squared is this distance squared. Take the square root. It's omega n. Go take a moment, pause the video, and square this side and see what you get. You're going to get omega n. So there's a lot of information here. If you know the roots, okay, so minus 3 plus or minus 3i, if you get the roots of your differential equation, you can go, wait a second, okay, this distance, this gives me time constant and settling time. This distance gives me the oscillation that's going to be caused by that root, okay? And here's the resonance that's there. But we can get more, okay? So let's look at this angle in here, phi, all right? What's the cosine? Adjacent over hypotenuse. So the cosine of phi is zeta omega n divided by omega n. Or the cosine of phi is the damping. And that's this measured right here. Okay, so if damping is the cosine of this angle, as this comes down here, that angle goes to 0. Cosine of 0 is 1. So all along the real axis, the damping ratio is 1. By the same token, as you rotate up to here, and you can't go over on this side because that's where it's not stable. It never settles. This is the side that the response blows up on. So as we take it up to here, damping right on here is 0. It never damps out. That's why it keeps on going. It makes complete sense. Okay? So right here, I was telling you to multiply these out. I do it right here, omega n squared. If you square this, you're going to get zeta squared omega n squared. Square this, you're going to get omega n squared times 1 minus zeta squared. These two will cancel. You're left with omega n squared. Just Pythagoras. All right? So we now see that the damping ratio ranges between 0 along here, meaning your response never damps out. Once it gets going, it keeps on going. And if it gets over here, it blows up. And then here, damping is 1. So we range here. How much damping? And so what you can start to see is that as soon as you get your characteristic polynomial and you get all the roots, here's what's happening. So everything's either a first order root or you have these complex second ones. And they can be repeated, but we're not going to worry about that. If as these roots move along here, okay, settling time changes. As we go along here, damping changes. Or a wrong thing, I meant a natural frequency gets bigger. And generally, as your natural frequency gets bigger, the system becomes more stiff. Well, that's a good mechanical property. All right, so this affects our time constant settling time. Radial distance out, we get more natural frequency, we tend to be more stiff. As we go from here down to here, we get more damping in the system. Okay, as these poles go higher, we get higher frequency oscillation. And so we can start to see for the next course, the controls course, that where these are placed tells you pretty much everything about how this system's going to respond. It's not quite everything, but it's a lot. Okay? Once you see which pole is the closest to the imaginary axis, the one that dies out last, that's telling you the main characteristics of your response. This pole location is massive. Okay? So do you think when you did your problems in your math course, they would give you, differential equation, you just had to solve it. But as you start to dig into what that equation is, the properties that lead to that solution, you can start to see where they come from. There's a tremendous amount of information here in this characteristic polynomial. And as we learn to analyze it fully, we're not going to have to solve the differential equation. Saves us a lot of time. All right, so that's where we're going to end on this video, and we will move on to forced second order systems comes next. We're going to start applying inputs to this thing. We'll see you then. Bye now.